China has started drilling one of the deepest holes in human history, and the goal reaches far below oil and gas. In 2023, China began drilling a 10,000-meter deep borehole in the Tarim Basin, which sits inside the Taklamakan Desert in the Xinjiang region. The total planned depth is 32,808 feet, which equals 10 kilometers. The project is led by the China National Petroleum Corporation, also known as CNPC. The location is one of the largest oil and gas producing regions in China. Engineers selected this basin because it contains very thick layers of sedimentary rock that preserve Earth's geological history. The drilling target goes through more than 10 layers of continental strata. Scientists want to reach rock formations that date back to the Cretaceous period. The Cretaceous period began around 145 million years ago and ended around 66 million years ago. Dinosaurs lived during this period, and major tectonic shifts shaped today's continents. Rock from that era can provide valuable information about climate patterns, fossil fuel formation, and crust movement. The depth alone makes this project historic. 10 kilometers is higher than the altitude at which many commercial airplanes cruise. Mount Everest stands at 8,848 meters, so the borehole will go deeper into the Earth than Everest rises above sea level. The deepest hole ever drilled remains the Kola Superdeep Borehole in Russia, which reached 12,262 meters in 1989. China's well doesn't break that record, yet it places the country among a very small group capable of drilling this deep. The engineering challenges are extreme. Temperatures at that depth can reach around 200 degrees Celsius. Pressure increases heavily as the drill moves downward. Rock formations become harder and more abrasive. Standard drilling equipment would fail under such conditions. China's engineers developed high-strength drill pipes and specialized drill bits designed for ultra-deep environments. The drilling system also uses real-time monitoring to measure pressure, temperature, and rock density. Data travels back to the surface so engineers can adjust speed and weight during drilling. Scientific research stands at the center of the official explanation. Geologists want to study Earth's internal structure in greater detail. Deeper rock samples can help scientists understand how tectonic plates behave beneath continental regions. Improved data may refine earthquake models. China experiences seismic activity in several provinces, so better geological mapping carries practical value. Researchers also want to analyze mineral composition and thermal gradients. Each layer of rock tells part of a story about Earth's past. Energy security forms another key reason for the project. The Tarim Basin already produces oil and natural gas, including some of the deepest onshore reserves in Asia. Ultra-deep drilling can reveal new hydrocarbon deposits that older technology could not access. China imports a large share of its energy, so expanding domestic production strengthens national stability. Deep exploration reduces dependence on foreign suppliers and lowers vulnerability to global supply disruptions. In 2021, President Xi Jinping called for increased exploration of deep sea, deep space, and deep Earth. This drilling project aligns with that strategy. The government views extreme environment research as a measure of technological strength. Mastering high-pressure drilling demonstrates industrial capability. Advanced drilling tools require expertise in metallurgy, materials science, and data systems. Success in one extreme environment often supports innovation in others. Now let us shift slightly from pure facts into a wider reflection. Picture a drilling rig standing in the desert under a bright sun. Workers monitor screens inside a control room while steel pipes descend deeper every day. Each meter takes effort. Each meter costs money. Below the surface, rock layers formed long before humans existed. The drill bit cuts through ancient seabeds that once held marine life. It passes through compressed sediments that trapped organic matter millions of years ago. The desert above remains quiet, yet far below the surface, the machine grinds through stone that has never seen light. Engineers track vibrations, geologists examine core samples, scientists record temperature readings. The process continues around the clock. Shifts change and the drilling continues. Equipment must endure constant stress. Maintenance teams inspect each component because failure at such depth would cause serious delays. Some experts compare this project to building a telescope aimed downward instead of upward. Astronomers look into deep space to understand cosmic history. Geologists drill into the deep Earth to understand planetary history. Both efforts require patience and advanced tools. Both push technology beyond common limits. China already operates a space station and conducts lunar missions, so deep Earth exploration fits within a broader pattern of scientific ambition. There's also a geopolitical layer. Global competition now includes control over advanced technology and natural resources. Countries that master ultra-deep drilling gain access to harder-to-reach energy reserves. They also strengthen domestic research industries. The United States, Russia, and Germany conducted deep drilling programs in the past. Few modern projects attempt such depths due to high cost and technical difficulty. China's decision signals long-term planning rather than short-term profit. Let us add a narrative thread here. A young geology student in Beijing reads about the project and feels inspired. She studies rock mechanics and hopes to join a future deep drilling mission. She understands that the borehole is not only about oil, she sees it as a gateway to knowledge about Earth's interior. Her professors discuss seismic waves, mantle heat flow, and crust deformation. Classroom theory connects with real equipment operating in the desert. Back at the drilling site, the borehole passes through another layer of sandstone, shale, and limestone. Each formation has its own density and fracture pattern. Engineers adjust drilling fluid to stabilize the well walls. High-pressure fluids circulate downward and carry crushed rock back to the surface. Technicians analyze the returning cuttings to identify changes in composition. Small variations reveal shifts in geological time. The Cretaceous target layer holds special interest. That period experienced high global temperatures and rising sea levels. Large quantities of organic material accumulated in certain basins. Over millions of years, heat and pressure transformed that material into hydrocarbons. By reaching these rocks, scientists can confirm models about how oil fields formed in the Tarim region. Confirmation supports more accurate exploration in other basins. Temperature management remains critical. At 200 degrees Celsius, metal weakens and electronic components face risk. Engineers use heat-resistant alloys and insulated sensors. Real-time data helps prevent sudden pressure spikes. Safety systems monitor gas levels. Teams follow strict procedures during every phase of drilling. Ultra-deep wells require patience. Rushing increases danger and financial loss. Let's bring a subtle fictional touch again. As the drill approaches deeper layers, the crew discusses what they might discover. One worker jokes about finding a hidden chamber from prehistoric times. Another replies with a smile and returns to checking pressure findings. The humor keeps morale high, yet everyone understands the seriousness of the task. Data from this well may guide research for decades. Economically, such a project demands heavy investment. Ultra-deep drilling often costs hundreds of millions of dollars. Equipment must operate for months without major failure. Each replacement part carries a high expense. The government supports the project because long-term scientific and energy gains outweigh immediate cost. National projects at this scale often serve as training grounds for future engineers. Environmental impact remains controlled through standard industrial measures. The borehole occupies a limited surface area. Engineers seal casing sections as drilling progresses to prevent leaks. Monitoring systems detect potential gas escape. Regulations require secure closure procedures once drilling is complete. Deep exploration does not involve large-scale excavation, so surface disturbance stays relatively small compared to open-pit mining. Now consider the symbolic message. Drilling 10 kilometers into the Earth sends a signal about confidence. It shows that a nation is willing to invest in complex science. It demonstrates trust in domestic expertise. Global observers notice such efforts. Technology leadership influences diplomatic strength. Energy independence influences economic resilience. As the borehole nears its planned depth, researchers will analyze core samples in laboratories across China. Specialists will measure mineral composition and microfossils. Seismologists will integrate new data into earthquake models. Energy experts will evaluate hydrocarbon potential. The well may not break the global depth record set by the Kola Superdeep Borehole, yet it represents a major step in Asian deep earth research. China's ultra-deep borehole shows that exploration no longer stops at oceans or outer space, because the ground beneath us still holds unanswered questions.